Thanks. Yeah. So today I want to talk about how to prove the Lichtenbaum-Cullen property. So we saw last time what it was and why it's so useful in proving the kind of statements you wanted to prove, to disprove the telescope conjecture. And so there's sort of two things I owe you. So namely the sort of the input, the computational input, I guess. Um, for disproving the telescope conjecture is uh, it sort of needed two additional statements that I haven't explained how to prove. Um, Two statements. So one was this redshift statement. So we needed to know that the objects that we're looking at are non-zero. So you need to know that TC of VPN, after you tensor with this Vn+1 with Vn+1 inverted, so a type n+1 the telescope of a type n+1 complex, we wanted to know that was non-zero. And then the other statement, which we reduced a lot of the proof to last time, was this uniform boundedness property of THH at the fixed points. So we wanted to know that THH of BPN, when you take the fixed points by some subgroup of the Adams operations acting on it, and you tensor with the type n+2 complex, we wanted to know that this is uniformly bounded in the T structure on cyclotonic spectra. So it's uniformly bounded in cyclotonic spectra. Okay, we just needed this for k sufficiently large. Okay, and this is called the uniform. It's the uniform version of the Lichtenbaum-Cullen property of height n. Sorry, this should be n+2. Right. Okay. So these are of height n. So these are the two properties that the key facts that I haven't explained the proof of yet, and I'm going to try to get to today. So maybe I'll just say number one, the fact number one, it's due to Ausonian Rogness for n equals 1 and p at least 5, and it's due to Hahn and Wilson in general. And I'm really just going to focus on this case. Okay, so we're interested in proving boundedness in cyclotomic spectra. So I want to tell you some important tools for thinking about boundedness. So part of the data of a cyclotomic spectrum is a spectrum with a circle action. So here's a property that a spectrum with a circle action has if it's bounded in the category of cyclotomic spectra. But it's also useful for proving boundedness. So here's the definition. So if you have a spectrum with a circle action, it satisfies what's called weak canonical vanishing. Or WCV, if the following thing is true. So there's this canonical map. You can take the fixed points by any subgroup of the circle, and that fixed points maps to the Tate construction. And the weak canonical vanishing is saying that this map is 0 in high degrees. So this is 0 for star sufficiently large, independent of k. So this should be independent of k, and k is allowed to be between 0 and infinity. So it's allowed to be infinity, in which case you're basically taking the fixed points by the circle, the whole circle. Okay. So that's weak canonical vanishing. Okay, so why so the claim is that this is going to be helpful. This property is going to be for a cyclotomic spectrum is going to be helpful improving boundedness in the category of cyclotomic spectra. But in fact, when you prove weak canonical vanishing, you often prove something stronger, namely strong canonical vanishing. So why would something like this be true? Why would this is some sort of pi star level statement? You could hope that there's some sort of spectrum level statement that would explain this, and that's what's called strong canonical vanishing. So if you have a circle equivariant spectrum, it satisfies strong canonical vanishing. If the following thing is true. So we're going to take your spectrum X, and you can look at its connective cover, like its B connective cover. That maps to X. And now what you can do is so this is a circle equivariant map. And you can compose with a map that I will call A lambda to the N. So it's the following thing. So there's the sphere with the trivial action inside circle equivariant spectra. And then there's the sphere, there's a two-dimensional sphere with an action given by a representation of the circle, namely lambda is sort of the standard representation of the circle. And there's the inclusion of the element 0 inside that sphere, and that gives you an equivariant map called A lambda. And so you can look at the nth tensor power of that map, which gives you a map from X to the n lambda suspension of X. And strong canonical vanishing asks that this map is 0 for n is 0 for n and b sufficiently large. Okay? And the point is that strong canonical vanishing implies weak canonical vanishing, because what is this saying? Well, the point is that this map is an isomorphism after you take the take construction, because the fiber of this map is acted on freely by it's a free finite complex, like the unit sphere inside this representation it has a free action, and so this map, when you take fixed points by any subgroup, will give you this canonical map in high degrees. And so it vanishes because this map was 0. Okay. So that's strong canonical vanishing. And then there's here's another definition. So if you have X in cyclotomic spectra, it satisfies the Siegel conjecture. And I'll just write that as Siegel. If the following thing is true, so you have this Frobenius map from X to X to the TCP coming from the cyclotomic structure, and you want the fiber of this to be truncated. So in other words, you want the Frobenius map to be an isomorphism in large degrees. Okay, so what was the point of introducing all these properties? The point is that they combined, they're essentially equivalent to boundedness in the category of cyclotomic spectra. So here's a proposition. So let's suppose that X is a cyclotomic spectrum, and let's assume just that X is bounded below, and P to the N is equal to 0 on X for some N. Okay, so this is going to be true of everything we care about. So then the claim is that if you look at the statement that X is bounded in cyclotomic spectra, that's equivalent to the statement that X satisfies either weak canonical vanishing and Siegel conjecture, or or strong canonical vanishing. Either one is fine, and Siegel. So in other words, these two properties of this canonical vanishing and Siegel conjecture are enough to prove boundedness in the category of cyclotomic spectrum. Okay, so we don't really need both directions of this equivalence, but maybe it's good to know. So the only direction we really need is that if it satisfies, let's say, weak canonical vanishing and Siegel conjecture, then you're bounded. So I'm just going to explain the proof of that. So proof of just one direction. So let's recall what boundedness means. So X is bounded above. That's equivalent to saying that TR of X is bounded above. And I defined TR last time as maps out of a certain cyclotomic spectrum, this L infinity of this LP infinity of the sphere. But there's really just a very explicit formula for this. So if X is bounded below, there's an explicit formula for TR. So then TR is just the following thing. It's the following thing. So you start with X, and then X has a map to X TCP via the Frobenius. And then, sorry, okay, let me just ignore this. Ignore the X is bounded below. So X has a map to the TCP via the Frobenius. And there's an X, if you take the fixed points by CP, that has a canonical map to X TCP. And so you can take this pullback, but now you're not done. So X HCP has a map to X TCP HCP squared mod CP via the fixed points of the Frobenius map. And then there's a canonical map from XHCP squared into that, and you can take this pullback. And then TR is basically defined as this infinite pullback, where you just keep doing this for larger and larger cyclic subgroups. So now the next thing you do is you look at TCP HCP cubed mod CP, and then there's a canonical map from HCP cubed, and then you sort of take this infinite iterated pullback. Okay. And so we're trying to show that this is bounded above, assuming, let's say, weak canonical vanishing. So we want to assume weak canonical vanishing and Siegel conjecture. So what we want to show is that this TR is 0 in really large degrees. So the point is that this infinite iterated pullback, we can think of it as an inverse limit of just doing finitely many pullbacks. So we can sort of cut off the pullback at like this stage, or this stage, or this stage, and so on. And you can take the inverse limit of just taking these finite amounts of pullbacks. And the point is that so this stage is called like TR1, and this is TR2. And I'm sorry if I got the indexing wrong. But so if you just take these finite pullbacks, then TR is equal to the limit of TRN. Okay. And so it suffices to show that TRN to TRN minus 1 is 0 on pi star in large degrees. Because that would tell you that you're taking the inverse limit of something that's 0 in large degrees, so it has to be, the inverse limit is bounded above. Okay. So how are you going to prove that? Well, the point is that's exactly, in some sense, the conditions that we have. So the point is that in large degrees, these maps from XHCP to the K, these Frobenius maps, these maps are isomorphisms in large degrees by the Siegel conjecture. I mean, if you take the homotopy fixed points of a map that's an isomorphism in large degrees, it's still an isomorphism in large degrees. And in large degrees, the canonical map, so weak canonical vanishing, says that the canonical map is 0 in large degrees. And so if you think about what these pullbacks are doing, you're basically just looking at like this map is essentially an isomorphism and this map is essentially 0. And so each of these transition maps in large degrees is just the 0 map on homotopy groups. And that's exactly what we wanted. Okay. So the point was that, right, so we have this equivalent way of thinking about boundedness in cyclotomic spectra. We want to show this sort of canonical vanishing statement that the canonical map is 0 in large degrees and that the Siegel conjecture holds, namely that the Frobenius map is an isomorphism in large degrees. Okay, so here's a tool that's very useful for proving canonical vanishing. The dilemma, let's say that R is a ring um, it's a ring with a circle action. Okay. And let's say that it's some power of p acts by 0. Okay. Then here's a way that you could try to prove canonical vanishing. So suppose you have an element inside pi k of R, which has the following properties. So R mod mu is bounded above. And then the second property is that mu is in the image of the transfer map. So there's a transfer map from, you can take the suspension of R and then you take the orbits by the circle acting on that. And there's a transfer map to R. And if mu is in the image of this transfer, that's the second condition we want, then the conclusion is that R satisfies strong canonical vanishing. Okay. This is just it's a nice way to tell when you have strong canonical vanishing. So here's the reason it's true. So what are we trying to show? We want to show that to show strong canonical vanishing, you want to show that for some choice of B and N, the following composite is null. So you map from R, the connective cover of some B connective cover of R to R, and then you use A lambda to the N to go to suspension N lambda R. So you want to show this is null for appropriate choices. Well, okay, so now what we can do is we can consider, so what the fact that mu is in the image of the transfer map, this transfer map, it factors through the homotopy fixed points of R by T. And so what that's saying is that mu actually, it refines to an equivariant self-map of R. So this implies that mu is in fact an equivariant self-map. Using this lift, you can get a map from the suspension K of R to R, which is an equivariant, a circle equivariant map, because of the fact that you just choose the lift that you had and then map it to here. Okay, so what you can do now is in the category, this whole diagram is in the category of circle equivariant spectra. So you can now consider multiplication by this mu. Maybe I'll give it a slight different name. I'll call it mu tilde, just to indicate that it's coming from this lift. Okay. And then you can look at R mod mu tilde. And the point is that this thing is bounded. This thing is bounded above because the underlying spectrum of this is just R mod mu. This is some circle equivariant spectrum whose underlying spectrum is R mod mu. And so if you choose B large enough, then this composite is 0 because this is highly connective and this is co-connective. And so if you choose B large enough, you get a lift like this. Okay. But on the other hand, mu is in the image of the transfer. And so what that's telling you is that mu is 0 in the Tate construction. But the Tate construction is exactly what you get on homotopy groups after taking the co-limit over all of these a lambda to the n's. So if you invert a lambda, that's at the level of the homotopy fixed points, that is exactly the Tate construction. And so what you learn, so I guess this p to the n equals 0 condition is just being used to make sure that homotopy groups commutes with filtered colimits, because if you work in p-complete spectra, that's not always true. But what you learn is that when n is large enough, this composite is also 0 because mu tilde was in the image of the transfer map. And so it's 0 in the Tate construction, and therefore it's 0. That null homotopy in the Tate construction can be realized at a finite stage. So this is for n sufficiently large. And this is, yeah. Okay. And so then you're done because you wanted a null homotopy of this composite, but this map factored through that, and then this is 0. Okay. So this is a nice way to prove canonical vanishing. Okay, so now I want to get into an example. So let's set n equal to 1, and let's say p to be large, like let's say at least 7 for simplicity. So now I want to explain how in practice do you prove these things about, or I want to give some sense of how do you prove these things about boundedness and so on. So let's first try to understand the following thing. So if you look at THH of BP1 and you tensor with a type 3 complex, in this case, I want to take our type 3 complex to just be the sphere mod P, V1, and V2, okay? So the Smith-Toda complex. So let's try to see why this is cyclotomically bounded. So bounded in the category of cyclotomic spectra. So we want to prove like this canonical vanishing and this Siegel conjecture. So let me just remind you briefly that the homotopy ring of this BP1, it's quite simple. It's just a polynomial ring over ABC localized at P, or P completed if you want, on V1. And so, in this THH, everything is P completed. So, okay, so maybe I'll just P complete it from the start. Why not? Okay, so there's an Adams filtration, which gives you a filtration on BP1, and the associated graded is just a polynomial ring over FP. So there's a filtration on BP1 that at the level of homotopy groups is just filtering by the P comma V1 adic filtration. And I'm going to refer to this filtration as BP1 fill. Okay. So now how can we use this filtration to understand THH? Well, what was THH? I mean, THH was just R tensored over R tensor R op of R. But that definition makes sense in any category, any symmetric monoidal category with enough colimits. So you can make sense of THH in some category C of some object R as just the same formula, some symmetric monoidal category as just R tensor over R tensor R op of R. That makes sense for any category C in algebra R. So we can now make sense of THH in filtered spectra of BP1 with its filtration. And this is going to be a filtration on the underlying spectrum being THH of BP1. And the associated graded of this filtration is just going to be THH of the associated graded, viewed as a graded ring. So namely THH of this polynomial ring over FP. Okay. And how do you understand this? Associated graded? Well, the point is that, again, THH is symmetric monoidal. So this ring just breaks up as a tensor product of two rings. Namely, it's THH of FP and then THH of the other factor, which is just a polynomial ring over the sphere. And again, using the symmetric monoidality of THH and the fact that this construction is functorial and symmetric monoidal colimit preserving functors, you can see that this is the same thing as THH of FP tensored over FP with THH in the category of FP modules in spectra of FP adjoint V0, V1. And this has another name. This is the Hochschild homology. Of FP adjoint V0, V1. And we know how to compute Hochschild homology of polynomial rings. There's a result of Hochschild-Konstantin Rosen that says that this is, it just looks like the algebra of differential forms on this ring over FP. And so what you learn is that pi star of, if you take pi star of this, what you get is pi star of THH of FP tensored over FP with the Hochschild homology of this polynomial ring, which is just FP adjoint V0, V1, and then two exterior generators coming from the differential forms, the differentials of these V0 and V1. So this is just my notation for exterior classes. Okay. So okay, so that's how you compute. That's how you would compute the associated graded of this THH of BP1. Well, okay, so I guess then you sort of need to know what this is. So it's a result of Bookstedt that this is just a polynomial ring over FP. So this is FP adjoins some class called mu0, where the degree of mu0 is 2. Okay. So let me okay, so we weren't quite interested in this because we really wanted to know THH of BP1 tensored with this V3. So let's do some version of tensoring with V3, which is modeling out by P, V1, and V2. So to do that, I'm gonna slightly change the filtered object we're gonna look at. So we're gonna tensor relative to BP1 fill with BP1 fill modulo P, V1, and V2, but I'm going to view P and V1 as having positive filtration. And so if I mod out by this having P and V1 and positive filtration, I just end up with an exterior algebra over FP on a class whose degree is 1 higher than V2. And so this tensor product gives you a filtration on this thing tensored with V3. Okay. And the computation of this homotopy ring is going to be the same, just slightly simpler, actually. So basically, you just need to tensor over this polynomial ring with FP with an exterior generator on this, where this map is essentially the 0 map. And so what you learn is that you essentially just get rid of these two polynomial generators and you add a new exterior generator. That's all you're doing by modding up. You're modding up by this V0, the V1, and you're adding this class because you modded up by V2, but it was already 0. So what you learn is that THH of BP1, the associated graded of this is just, it's a polynomial ring on mu0, and then there are 3 exterior classes. There's dv0, dv1, and then sigma of v2. Okay. So now there's a spectral sequence whose E1 page is this, and that converges to the homotopy groups of THH of BP1. So the spectral sequence is coming from the fact that you have this is the associated gradient of a filtered object. Okay, so what happens in the spectral sequence? I won't justify myself here, but I'll tell you what happens. So there are two differentials that determine everything up to the Leibniz rule. So this mu0 has a differential that hits the element dv0. And then its pth power also has a differential, and that hits dv1. Okay. And up to Leibniz rule, these determine all the differentials up to the Leibniz rule. Okay. And so the conclusion of all of this is that pi star of THH of BP1, oh, sorry, everything here was tensored with V3. V3. So pi star of THH of BP1 tensored with V3, it looks like the following thing. It's a polynomial ring on a class I'll call mu2. And then there are three exterior classes. There's lambda1, lambda2, and then sigma v2. And then I'll tell you how these correspond to things in the spectral sequence. So this mu2 is detected in the spectral sequence by mu0 to the p squared. So mu0 to the p squared was a permanent cycle in the spectral sequence. It didn't have any differentials. And then lambda1 is detected by mu0 to the p minus 1 times dv0. And then lambda2 is detected by mu0 to the p times p minus 1 dv1. Okay. So right, so this is how you'd compute the homotopy groups of this THH. You'd run the spectral sequence. That's one way to do it. That's the simplest way I know of, really. So what you can do now is okay, so once you know the homotopy groups, so what we're interested in, we were interested in proving like the Siegel conjecture, for example, which was the statement that the Frobenius map on the cyclotomic spectrum is an isomorphism in large degrees. And so how do you prove this? So here's sort of the key proposition. So, which implies the Siegel conjecture, which is that you can look at this Frobenius map from THH of BP1, tensor V3, to the Tate construction. And the proposition is that what it does is essentially it just inverts this mu2. So in other words, this is a ring map, and it factors through what you'd get by inverting mu2 on the source. So you can take this source and you can just invert mu2. And then that maps to here, and this map is an isomorphism. And so note that this implies the Siegel conjecture for THH of BP1 tensor to V3. Because what it's telling you is that the homotopy groups of the target are just obtained by taking this ring and inverting mu2. But you can see that in large degrees, any element of this ring after inverting mu2 just has to have a positive power of mu2. And so what that's saying is that in positive degrees, or in large degrees, this map, the map that's given by inverting mu2 is just an isomorphism on homotopy groups, and that's the Siegel conjecture. Okay, so this is the reason for the Siegel conjecture. It's because the Frobenius map is essentially just inverting a class. And here's the proof idea, I guess. I'm not gonna give the proof, but the proof idea is that you want to check this at the level of the associated graded. So you can check this claim, check the proposition for the associated graded of the filtration. And it's much easier to check on the associated graded because now you're just looking at THH of a polynomial algebra over FP. So, i.e., you just want to check it for THH of this polynomial algebra over FP. Okay? And so the claim is that's much easier. So maybe I will give an example of what the Frobenius map looks like for THH of FP itself. So like if you just look at THH of FP, so let's recall that the homotopy groups of that, let's look at THH of FP mod P, okay? So mod P, the homotopy groups of that are just, they look like, well, okay, maybe I won't run out of P actually, sorry. So the homotopy groups of this, recall, was just a polynomial ring on a single generator over FP, mu0. And in the Tate spectral sequence, so there's a Tate spectral sequence for computing the Tate construction on this THH of FP. So there's the Tate spectral sequence, and this Tate spectral sequence, the E2 page of it is it's exactly the homotopy groups of THH of FP, and then you have to adjoin an invertible class in degree -2, and you have to adjoin a class epsilon in degree -1, which is an exterior class. This is the Tate cohomology of the group FP, the group CP. That's what this is. So there's a Tate spectral sequence that converges to this. And it has a differential, which is that d of epsilon is equal to mu0 times t squared. Okay? And so, right, so that's really the only differential in the spectral sequence up to the Leibniz rule. And the Frobenius of this mu0 is detected by T inverse. And you can see that the E infinity page of the spectral sequence is just it's just FP adjoin T plus or minus 1. Because the epsilon sort of cancels out with this mu. Okay. And so you can see that the Frobenius map is exactly just inverting mu. It's just sending mu to the inverse of T. And so this is just the ring that you obtain by inverting mu. It's a Laurent polynomial ring. So that's what the Siegel conjecture looks like for THH of FP. And the claim is that you can kind of just check on associated graded. Well, you can check that it works for polynomial rings too, like this, and that you can check this on the associated graded of the filtration. Okay, so now how do you continue? Well, so now the point is that you can try to use, so now because of the Siegel conjecture, you know what the Tate construction of THH of BP1 TCP tensor V3, you know what this looks like. You know its homotopy ring. Its homotopy ring is just this ring, but then you invert mu2. So now you can try to reconstruct, to reverse engineer the Tate spectral sequence for THH of BP1 tensor V3, and Tate CP. So you can try to figure out what the Tate spectral sequence is because you know what it converges to. You know the homotopy groups of what the spectral sequence converges to. And so there's a key input that you need, which is the following. So the key input is that the element. So what you need to know is that in THH of BP1, TCP tensor V2. Let's see, do I want to say it like this? Maybe I'll say Tate, if you take the Tate construction with respect to the circle and you tensor with V2, then you need to know that the element mu2 times T detects V2. So the element V2 coming from the sphere, the homotopy groups of the sphere mod P and V1. So there's this key fact, and what this key input tells you is that there's a differential in the Tate spectral sequence where the differential on sigma V2. So sigma V2 is the class that was trying to be the null homotopy of V2. And so its differential in the spectral sequence should be V2. It should be trying to hit V2. But now we know that if we know that V2 is detected by this class, then what that's saying is that the differential on sigma V2 should be mu2 times T. So this is a key differential that you need to know. But then the others you can kind of reverse engineer and figure out that there are these other differentials that look like this. It's not so important. I'm just going to write them down. Okay, so there's some differentials like this. And let me explain why you're kind of done at this point. So first of all, I claim that this fact already implies that I claim already that TC of BP1, if you tensored with the telescope of a type 2 complex, then it's non-zero, which is one of the facts that we wanted to prove anyways. This is this redshift fact. So it implies that this is non-zero. And the reason is because this is a ring, and this ring maps to this ring. And you can see that in this ring, V2 it's non-zero, it's detected by this thing, but in fact it's not even non-zero, it's non-nilpotent. Like this is a non-nilpotent element inside the spectral sequence. And so when you invert V2, you still get something that's non-zero. So you can use that to see that this redshift statement. So this is sort of the key fact that you need to know. But then we actually learn more. So I claim we also learned the canonical vanishing. And that's for the following reason. So we have this differential, right? But we can just multiply this differential by T inverse. And so what you learn is that the differential on T inverse times sigma V2 is mu2, okay? And in the Tate spectral sequence, if you have a differential, this has a negative power of T, and this thing has a non-negative power of T. It's the T to the 0, I guess. So in a Tate spectral sequence, whenever you have a differential going from something with a negative power of T to a positive power of T, that differential is coming from the transfer map. So the negative powers of T, they exactly correspond to the homotopy orbits of your spectrum. And the non-negative powers of T correspond to the homotopy fixed points. And this differential is exactly corresponds to the transfer map. And so this differential tells you that mu2 is in the image of the transfer. And in fact, this is for the cyclic group of order P, but the same argument actually works for the whole circle group. And so you can actually see that it's in the image of the whole circle transfer. And so that this implies that you have strong canonical vanishing, because if you take THH of, if you take this to be our ring, so tensor with V3, if you just call this R, then R mod mu2 is bounded, and mu2 is in the image of the transfer. And we saw before that those two properties imply that you have strong canonical vanishing. That was this. Let me go up here. That was this lemma over here. That if you have R mod mu bounded and something in the image of the transfer, then you get strong canonical vanishing. So okay. So now because we have strong canonical vanishing, and we also I sketched the Siegel conjecture for BP1. What you learn is that exactly what we wanted. So you learn that THH of BP1 tensor V3 is cyclotomically bounded. Okay. So now the thing I still have to explain to you is how to bootstrap this to the fixed point. So what we really wanted to know, we wanted that THH of the BP1 fixed points by these Adams operations, and tensored with V3. We wanted this to be cyclotomically bounded uniformly, like uniformly in K, for K sufficiently large. So that's what we wanted to know. So first, we need to prove the Siegel conjecture and also canonical vanishing for this. And I'll just say the Siegel conjecture is actually quite similar. So Siegel conjecture, you can prove it quite similarly. So let me explain how. So there's a filtration on BP1 fixed points by P to the KZ. And here it's a very silly filtration. So what you do is you take the original filtration that you had on BP1, the Adams filtration. I'll just call that BP1 fill. And the point is that the Adams filtration is equivariant for any action you could possibly put on BP1. And so you can just take the fixed points of this filtration. And that gives you a filtration on this ring. And the associated graded is, it's a fixed points of the polynomial ring. So you take FP adjoint V0 and V1. But in fact, on the associated graded of the Adams filtration, the Adams operations act trivially. And so you just get the fixed points by a trivial action, which is this BP to the KZ. And so you can prove the Siegel conjecture on associated graded, and then use the same trick. So namely, you can reduce the Siegel conjecture for this to the Siegel conjecture for this ring, which is much more manageable. Okay. So I won't say much more about the Siegel conjecture. But then you wanted to prove canonical vanishing. So before getting into that, let me just mention that you can in fact completely understand pi star of this. So like we have this filtration, and so you get a spectral sequence. So what is THH of this FP adjoint V1, V0, V1, BP to the KZ? Well, it's it's just THH of FP adjoint V0, V1, and then you tensor with the THH of the sphere to the BZ, which is this thing that we studied in the second lecture. And the point is we need the homotopy groups of this. So okay, so let me mod out by V0, V1, V2 here. So then you can mod out by V0 and V1 and V2 here. And what you learn is that this is just the thing that we were previously looking at, so previously when we were looking at just BP1, we had this mu0, and then we had these three exterior classes, dv0, dv1, and sigma v2. And now you get some new terms coming from here, but it's quite simple what it adds. Namely, it adds a copy of the continuous functions of ZP with coefficients in FP, and an extra exterior class coming from the cohomology of a circle. So that's the class called zeta, which is coming from the cohomology of a circle. So zeta is in degree -1. Okay, so the point is that you can run the exact same spectral sequence that we were running to compute THH of BP1 to compute THH of this fixed points. And the only thing that changes is that you have this zeta and you have this extra continuous functions in ZP. And so after you make K sufficiently large, what you can see is that the spectral sequence maps to the spectral sequence for BP1. And so what you can learn is that for K sufficiently large, the differential, like you have similar differentials, namely differential on mu0 looks like some continuous function on ZP times dv0. So this was sort of the differential that we had when computing THH of BP1, and then similarly differential on mu0 to the p is some function times dv1. But the point is that I'll call it g maybe. The point is that f and g, they have the property that when you evaluate on 0, you had better get 1. Because when you evaluate at 0, you exactly get what the spectral sequence would have been for BP1. And so, but then f and g are continuous functions, and so that actually tells you that f restricted to p to the k zp is equal to 1, which is also g restricted to p to the k zp for k sufficiently large. Because if you have a continuous function whose value on 0 is 1, it's a locally constant function, and so it has to be constant on some p to the k zp for k sufficiently large. And so what this tells you in the end is that at the level of homotopy groups, this THH of BP1, if you make K sufficiently large, it already looks like the action was trivial in the sense that pi star of THH of BP1, HP to the KZ, tensor V3, it's just the same thing as THH pi star of the thing without the fixed points. And then you just tensor with the continuous functions on ZP, and then you add this extra zeta, this exterior class on zeta. And that's all you're doing for K sufficiently large. So it kind of looks the same as it would have looked for the trivial action. Okay, so this is good for the following reason. So recall that we have an element mu inside of here, right? We have an element mu, this mu2. This is this element that we used to prove canonical vanishing. Sorry, this should be p to the k zp, not just cp. Okay, so we have this element mu2, and this mu2 has the property that, well, co-fibering by it on THH of BP1 gives something bounded above. And it has the property that it's in the image of the transfer. So I want to claim that if you just consider like the element mu2 tensor 1 inside of, I'll just call that mu, inside of pi star of THH of this thing, I want to claim that this also satisfies the properties that we need to prove this canonical vanishing when K is sufficiently large. This satisfies, So let me give this a name. I'm going to call this RK. So RK mod mu is bounded above. So that's not hard to see. That's just because we know what the homotopy ring of this is. And this thing, when you mod out by mu, gives you something bounded above, and then you're just adding something that's only in a bounded range of degrees, so it's not going to change that. So that's fine. But then the slightly more subtle thing is that mu is in the image of the transfer map of transfer for k sufficiently large. So why is that? Well, if you take the colimit over k, so what are we looking at? We're looking at the transfer map. So that's we're looking at RK, the suspension of that homotopy orbits by the circle mapping to RK. And we want to show that mu lifts eventually lifts up here. But what we know is that if you take the colimit of RKs, so the colimit of RKs was just this thing that we were calling R before, which is THH of EP1 tensor with V3. And we know that the image of mu along in this colimit is just the previous thing that we knew was in the image of the transfer. So at the level of this colimit, mu did lift. Oops. Yeah. So we have this diagram like this where in the colimit, the image of mu lifted. But now this homotopy orbits commutes with co-filtered colimits. And so the fact that you had a lift at the level of this colimit tells you that you have to have a lift at some finite stage. So for some k sufficiently large, and in fact all k sufficiently large, you're going to have a lift of mu. Sort of because the homotopy orbits commutes with filtered colimits. You get a lift of mu for k sufficiently large. So this is like it's just a compactness argument. And so what you learn is that well, you learn that mu has these properties for k sufficiently large, and therefore by the lemma from the beginning of the lecture, Rk is bounded for k sufficiently large. And then if you examine the proof, you'll see that you in fact prove that it's uniformly bounded. The proof wasn't really insensitive to k. And that was exactly what we wanted. Yeah, so I mean, I have 2 more minutes. I had something else I could say, but maybe I will just stop here.